Hello, and thank you for watching my video. In the last video, part one of this overview of quadratic polynomial number theorem, we covered the generalization over the two parameters alpha and beta. In this video, we're going to take a look at what happens when we set alpha equals 1, beta equals 1, which was excluded from our case before. So for more information, see the online Encyclopedia of Integer Sequences, sequence A347187. Okay, on to the topic of this video. Okay, on to another topic. An important one is, what is P11 of n? Before we had alpha not equal to beta, but what if alpha does equal beta, and in particular the alpha equals 1, beta equals 1 case? Well, if we apply that to our quadratic, we get this sequence here, which is 2 copies of the square, symmetric about the 0. And so these would be the 4 gonal numbers, or maybe quadrigonal, I'm not sure, or the square numbers. And when we plug that into the generating function, we get this, which reduces to this, or also equivalently is equivalent to this. They would not be in a finite capacity. It's only by taking these generating functions to infinity can this equivalence be established. But it does mean to a finite limit. A sequence, you could use the sequences up to some finite limit and get correct results up to a finite limit. So in terms of sequences, this product, or this generating function, if it were just the denominator, then we know that would generate the function, or the sequence of the partitions. And this 1 plus qk is of course also widely known as being the generating function for partitions into distinct parts. So if we took the sequence of partitions into distinct parts and we multiplied it by the sequence of partitions, unrestricted partitions, then we would get the sequence of this generating function, which is called over-partitions. This generating function was studied by McMahon in the early 1900s, but it wasn't until really 2004, the paper by Corteil and Lovejoy, that there's been a resurgence in research around over-partitions. So that's why we exclude it from the first case, because it doesn't really belong there. It's a whole new function. It's we have partitions and then over-partitions. Now obviously they're related, and here's a way to get to them from one to the other smoothly without even knowing it. So P11 of n is the over-partitions of n. So now that we have over-partitions of n as the special case of the generalization of partitions, we can say, well, what if we took over-partitions of n and generalized that over the very same alpha beta? Of course we can do that. Nothing is stopping us. It's just as simple as this. And we end up with, just as before, the standard function over partitions of n is given by the generalized function when alpha equals 1 and beta equals 2. So now we are back on a recurrence, a cycle, where we can say, well, what is over partitions 1, 1 of n under the generalized over partitions function? Well, the answer is easy enough to compute. And we don't know what to call it, but let's call it 2 over partitions. I mean, it's new. There's nothing, nobody's studied this before. Didn't know it existed until now. So just to call it the 2 over partitions, and that the 2 over partitions function will be given by the alpha equals 1, beta equals 1 case of the generalized over partitions function. And in this case, the generating function reduces to this very nice form right here. It's not so pretty for 3 over partitions and beyond, but manageable up to small levels. I wanted to say degrees, but I think levels is probably a better way to say it. So we're getting this sort of picture here where partitions are the zero level partitions, and over partitions are 1 level partitions, and these are the 2 level or 2 over partitions, 1 over partitions, and regular partitions would be 0 partitions. zero level partitions, something like that. And then we can do this rinse and repeat all day long for as long as we want. So we could anticipate that this table, we could grow this table and have a sequence of a non-decreasing sequence going down each column, and also noting because at each column we have a generating function that's giving it. We could take Q real, and we could probably then, if we understood, we could solve these by hand and do this, and we can get we should be able to get a real valued function that describes these columns. And what that would do for us would be, well, in order to be super useful, we have to know what the heck is going on. What does it mean to be 2 over partitions? Now, so that's where this is at. Before we go crazy, let's figure out what it means. We have a combinatorial explanation for over partitions, but we don't have a combinatorial explanation for 2 over partitions, and but we try to find one, and it's difficult. The regular over partitions, these are n, these are partitions of n, are described by Cortiel and Lovejoy as you take a part and the first occurrence may be overlined, and then some more stuff. But basically it boils down to is like take the partitions of 3, for instance. Each partition counts, the over partitions function counts each partition to start with. So it's going to start with 3, 2, 1, and then 1, 1, 1. And then looking at 3, what parts may be overlined? Well, the 3 may be overlined, so we get another over partition. For 2, 1, we can overline 2, or we can overline 1, or we can overline both, and those are the only possibilities there. For 1, 1, 1, we can overline 1, but then we can't do anything else because it has to be the first occurrence only. In other words, the parts that may be overlined have to be distinct partitions. So any repeaters within a partition, forget about them, and we're working on just the distinct parts within a given partition. So in the example of n equals 4 with p of n equals 5, there's a mistake here, by the way. This should really be one entry, or each of these two should be bracketed. So however you want to do it, it's 1, 2, 3, 4, 5, blah, 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 14. And so that's how over partitions work, and that's a perfectly reasonable combinatorial explanation of what it means. Doesn't tell you why it's important, but anyway. So we can try something like that for 2 over partitions, and here's one scheme where I think basically what I did is I said, well, take each over partition as a distinct element, and we'll count them, and then we'll count by parts that may be underlined, sort of in a similar fashion. And there's some tweaks and some variances of this scheme, but I could never get it to work, could never find a reasonable explanation. And in this example, we should have got 24 here, but we get 26, but then we can modify some assumption and make it 24, but then that wrecks something over here, but it doesn't matter. All the ones I've tried go horribly awry in short order when you increase n. So anybody who wants to take up this challenge and figure this out, please do let me know. It could be very important. Just would share here, because another way to possibly establish what's going on with 2 over partitions, 3 over partitions, etc., would be expressions in equation-based forms like this. And this is just a sweet little theorem that I'm sure it's not a big deal. It's really a lemma, or it's just an observation. But I found it, and I thought that it was cool. That basically, because of the way the overlining method works, what you're doing is restricting to the distinct parts of a given partition of n. So the lambda I that are distinct are the only ones we're working on, so if that's the case, it's a set and not a multi-set. So if I have 5 distinct parts, there are going to be 2 to the 5 or 32k subsets of the composition, unique compositions of those parts. So you end up always with just take the number of distinct parts and then take 2 to its power to give you the number that it contributes to total over partitions for n. So 3 has one distinct part, 2 to the 1, 2 and 1, 2 distinct parts, 2 to the 2, and then 1, 1, 1, only one distinct part, so 2 to the 1, 2 plus 6 plus 2 is 8. Over partitions of 3 is 8. And so that's kind of cool. In part 3 of this little overview series, we're going to get into triangles, partinomial coefficients triangle, and how it relates to Pascal's triangle, and how these partition and these partition functions and sigma functions may be computed directly off of these triangles, and that when we do the same thing on the Pascal's triangle, we get corresponding alpha beta generalized Fibonacci numbers. So the next part in this little series, follow-up series, is coming up next. Please watch that. Thank you for watching this video. Please like and subscribe to my channel, and please click on the PayPal link to contribute to my mathematical research. Thank you again, and God bless you.